Okay, so in this video, what we're going to do is look at the second theorem of Laplace, which is very straightforward. It's just when you, instead of finding the Laplace transform of f of t, we're going to be looking at the Laplace transform of f of t times t, or f of t times t squared, or t cubed, or t to the n. But the most common example is the simplest case, where it's just going to be f of t times t, and we're looking at the Laplace transform of that. So if we have a look formally at what this is going to look like, we want to know what the Laplace transform of t times f of t is. Okay, and remember, we're always assuming, just for notation, that the Laplace transform of f of t equals f of s. Okay, whatever that is. So let's do our standard procedure, which you're familiar with by now. So we can say that the Laplace transform of t f of t is going to be equal to the semi-infinite integral of t f of t e to the minus st dt. So again, it might look a little bit scary at first, or maybe do integration by parts or something like that, but there's actually something that if you looked at it for long enough, you'd realize there's something very clever we can do. There's anyone who's very observant. What we can see is that there's a function and derivative going on here. So if we take the derivative of e to the minus st, okay, with respect to s, we actually end up with something that we could perhaps make a substitution with. Let's have a look. So if we take, if we do d by ds of e to the minus st, that will give us minus t e to the minus st. Well, oh look, that's very similar to t e to the minus st. So if we multiply each side by minus 1, we end up with minus d by ds of e to the minus st equals t e to the minus st. And that is a substitution we can make over here, because we've got t e to the minus st. So if we make that substitution, we can say the following. I'm going to do t e to the minus st, okay, after f of t. So I'm going to put f of t in over here. And then I'm going to say minus d by ds of e to the minus st dt. Okay? And now what I can do is take out the d by ds, or the negative d by ds, minus d by ds out of the integrand. And then say f of t e to the minus st dt. And oh look, that is f of s. That's our original Laplace transform of f of t, isn't it? The semi-infinite integral of f of t e to the minus st dt. So we can say that this is equal to minus d by ds of f of s. Or, in other words, we can say that's going to be equal to minus f prime s. And that's going to be the Laplace transform of t f of t. Okay? So it's as simple as that. So anytime you have a Laplace transform of a function multiplied by t, it's just going to be equal to the first derivative of f of s, whatever f of s is. So you would just find the Laplace transform of f of t, and then differentiate that, and times it by minus 1. So, so let's have a look at an example. Let's have a look at, let's say we have the Laplace transform of t sine 2t. So again, we have the second theorem going on here. Remember, the first theorem was a shift theorem, which was if you have a function multiplied by e to the minus at. But here we have times by t. So this is on the second theorem. The second theorem is that the Laplace transform of t times a function. This is going to be the original Laplace transform of that function, and then you take the first derivative of that and multiply it by minus 1. So we know that the Laplace transform of sine 2t equals 2 on s squared plus 4. And then if we take the first derivative of that, So if we use the quotient rule, remember just to go over that, if we say y equals uv, dy by dx, or any variable, is going to be v du minus u dv on v squared. So I'm going to use that here, and then say, and remember this is equal to f of s, yeah? Standard notation. Therefore we can say f prime s is going to be s squared plus 4 times the derivative of 2, which is 0, minus 2 times the derivative of the denominator, which in this case is going to be 2s, all on v squared, which is s squared plus 4 squared, yeah? And that's going to be equal to minus 4s on s squared plus 4 squared. Therefore, we can say that the negative of that, minus f prime s, is going to equal 4s on s squared plus 4 squared. And there we have it. And that's the answer. Whoops, sorry. I'm not very good at this. And that's going to be the answer to the Laplace transform of t times sine 2t. 4s on s squared plus 4 squared. Okay, let's do another one. Let's do the Laplace transform of t cosh 3t. So again, the second theorem. Again, you'll recognize these theorems very quickly when you do a few questions. There's only a couple of them. And again, really, the first one comes up a lot more than the second and third. But let's have a look at this one. So when we've got t times the function, we can say that the Laplace transform of t, f of t, equals minus f prime s. So let's find f of s, the Laplace transform of the original function, which is cosh 3t. So we can say that the Laplace transform of cosh 3t equals s on s squared minus 9. I think that's right, yeah. And then this is going to be equal to f of s, yeah. So f prime s, the first derivative of this with respect to s, is going to be equal to s squared minus 9 times 1 minus s times 2s, I think, over s squared minus 9 all squared. And that's going to equal to s squared minus 9 minus 2s squared, all on s squared minus 9 squared, which equals s squared minus 2s squared is going to be minus s squared minus 9, all on s squared minus 9 all squared. So we can therefore say that the negative minus f prime s is going to be equal to s squared plus 9 on s squared minus 9 all squared. Now, what we can do is we can take this a step further, and we can ask the question, well, what would the Laplace transform be of t squared cosh 3t? Well, to answer that, what we can do is that we can say, well, what this really is t times by t cosh 3t, isn't it? It's just another application of the second theorem, t times a function. And we already know what the Laplace transform of t cosh, sorry, it's not cosh, it should be cosh 3t is, because we've just worked that out over here. So if we do that again, we're going to end up with an answer that should be correct for t squared cosh 3t. And I'm not going to do it because I just can't be bothered, to tell you the truth, with the algebra. But if you do it, it will work. And then if you do it again, you can get t cubed times the function. So what you end up with is a generic form of the second theorem, which looks like this. The Laplace transform of t to the power of n, f of t, equals minus 1 to the power of n dn by dsn f of s. And that will give you the second theorem of any function for any power of t, which is really just an extension on saying that the Laplace transform of t f of t equals minus f of s. Okay, so again, you're only going to need to use this if the power of t is higher. If the power of t is, say, 2, you could just perform this twice. You could just perform this twice, but this will get you there. So it's just really a case of working out the derivative of the function to whatever power. In fact, coming to think about it, higher powers of 1 may actually necessitate using the quotient rule multiple times, unless there's an easy way of doing it. But I think generally speaking, the question won't require, hopefully, more than t f of t, rather than any higher power. Now that's it.